Good afternoon. My name is Sarjana Alam, and I am an undergraduate research student of Dr. Esme Dijke at the University of Alberta. Today, I will be sharing a brief introduction to our project where we have investigated the cryopreservation of regulatory T cells for therapeutic purposes and the role that cryoprotectant agents can play in that process. As we know, many clinical populations require immunosuppressive treatment, including transplant recipients. Receiving a transplant is a life-saving procedure, but subsequent suppression of the immune system is necessary to avoid graft rejection. Current methods for immune suppression include harsh anti-rejection drugs, which can be associated with morbidities. T regulatory cells, or Tregs, are the natural mediators of the immune system and can suppress unwanted immune reactions. Thus, there is great interest in exploiting that immunomodulatory function for tolerogenic cell therapy. Early phase clinical trials are underway and show great promise. However, to proceed to widespread clinical implementation, it would be beneficial to have an off-the-shelf allogeneic therapeutic Treg product available. Cryopreservation, or freezing of cells at very low temperatures, is the procedure that would allow for the aforementioned off-the-shelf product to be produced. The therapeutic Tregs could be prepared whenever the opportunity arises, stored long-term via cryopreservation, then thawed for use when there is a clinical need. However, the currently used Treg cryopreservation protocol has been adapted from protocols for other types of cells and is not customized for Tregs. Consequently, post-thaw outcomes are very poor. Only 40 to 70% of cells that were prepared can be recovered, and recovered cells have reduced Treg function. Overall, we lose essentially half of our usable cells in this process, and that poses a significant barrier for clinical implementation. Cryopreservation involves freezing cells in a cryoprotectant, a medium which can protect cells from ice crystal-induced damage at those very low temperatures. Treg cryopreservation uses 10% dimethyl sulfoxide, or DMSO, which is known to be highly cytotoxic. We hypothesize that the use of 10% DMSO is a significant contributing factor to the poor post-thaw outcomes that are currently seen. Using different cryoprotectants, which are less cytotoxic, including ice recrystallization inhibitor and dextran, may therefore allow for significant improvement. Our project aims to define the toxicity of cryoprotectant agents to Tregs, as even for common and well-studied agents like DMSO, there is limited understanding of how they interact with Tregs specifically. An additional objective is to understand how well Tregs are able to recover after being cryopreserved and eventually thawed. Answering these questions will be the first steps in a larger effort to determine how we can optimize Treg cryopreservation and to make cell therapy more cost-effective. In this project, we studied several different cryoprotectants, including the base media in which all other cryoprotectants are made. This solution acts as our control as it contains no cryoprotectant itself. Then we have the current standard 10% DMSO, 5% DMSO alone, 5% DMSO with ice recrystallization inhibitor, and 5% DMSO with 5% dextran. Ice recrystallization inhibitor is a new carbohydrate-based cryoprotectant manufactured by Panthera Cryosolutions, and dextran is a polysaccharide which is known to have cryoprotectant properties and has commonly been used for cryopreservation of other cell types. To conduct our investigation, we used both peripheral blood Tregs and thymic Tregs. Here we have 3 peripheral blood Treg samples and 4 thymic Treg samples. Peripheral blood Tregs were collected from adult volunteers and thymic Tregs from thymus tissue that is routinely discarded during cardiac surgeries of pediatric patients. Cells were expanded in culture by our customized 13-day Treg expansion protocol, then collected for experimentation. Throughout our experiments, we monitored the Treg phenotype expressed by our cells with flow cytometric analysis. To test the toxicity of our 5 cryoprotectant agents, we suspended the expanded Tregs in them, then incubated at very moderate temperatures, 22 and 37 degrees Celsius, for 2 to 4 hours. After this brief exposure period, we used an automated cell counter to look at cell numbers and viability. To calculate the recovery of Tregs, we simply compare the number of live cells before the exposure period to the number of live cells after the exposure period. Recovery of cells can therefore be considered a measure of the toxicity of the cryoprotectant. The graph on the top shows the recovery of cells after 2 hours of cryoprotectant exposure, while the graph on the bottom shows recovery after 4 hours of exposure. Blue data points represent recovery of cells exposed to the base solution, which is our control, and the green, purple, and orange represent 5% DMSO alone with ice recrystallization inhibitor or with dextran, respectively. We saw no significant differences from the control condition, indicating that these three alternate cryoprotectant options, which we're exploring, are not significantly toxic to Tregs. However, where we do see a significant drop in cell recovery is for Tregs exposed to 10% DMSO, the current standard, at 37 degrees Celsius. After 2 hours, recovery drops to 49%, and after 4 hours to just 11%. These results demonstrate that the current 10% DMSO is cytotoxic to a concerning degree at higher temperatures. We were also interested in assessing the cryoprotection afforded to Tregs by each cryoprotectant. To do so, cells were suspended in cryoprotectant, then immediately transferred to a negative 80-degree freezer to undergo controlled rate freezing at a rate of 1 degree Celsius per minute, then transferred to liquid nitrogen for long-term storage. When they were retrieved at a later time, they were rapidly thawed in a 37 degrees Celsius water bath. This graph shows post-thaw recovery of Tregs. In other words, the percent of live cells initially frozen that remained viable after thawing. As expected, the base solution, our control condition with no cryoprotectant, resulted in a very poor median recovery of 9%, confirming the necessity of a cryoprotectant's presence. The median post-thaw recovery of Tregs frozen in 10% DMSO, the current standard, was 70%, which is just as earlier literature suggests. Notably, we saw no significant differences between 10% DMSO and the other three cryoprotective agents, indicating that the cryoprotective function of 5% DMSO is on par with that of 10% DMSO, whether it is alone or in combination with ice recrystallization inhibitor or dextran. We were also interested in the more long-term post-thaw outcomes resulting from each cryoprotectant. Therefore, after thawing the Tregs, we cultured them with or without low-dose interleukin-2 or IL-2, a Treg growth factor, and monitored growth and viability for 48 hours. Although Tregs cryopreserved in the base condition without cryoprotectant struggled to recover, cells frozen in the other cryoprotectant solutions expanded reasonably well post-thaw. There were no significant differences between cryoprotectants after 24 hours in culture, which we can see on this slide, and the same remained true after 48 hours. To ensure that our Treg isolation and culture were successful, we checked the phenotype expression of our cells on the first and last day of expansion with flow cytometry. CD25 and FOXP3 are markers for Tregs, so when we saw that 88 to 94% of our cells were CD4 positive, CD25 positive, FOXP3 positive after isolation, this confirmed good purity of the cell population. And that purity was maintained after expansion as well. The image on this slide shows data from one representative sample where dot plots have been gated on viable CD4 positive T cells to find the Treg population. We used the same flow cytometric methods to check samples collected 0 and 48 hours after thawing, after they had been cryopreserved in different cryoprotectants. Again, we saw that the Treg phenotype was maintained quite well, both immediately after and 48 hours after thaw, and this was true of cells frozen in all cryoprotectants, as we can see. Ultimately, the experiments that we've conducted thus far and which I've shared today show that lowering DMSO concentration may be an important measure in improving Treg cryopreservation protocols. What we've seen suggests that 5% DMSO alone with ice recrystallization inhibitor or with dextran seems to have a cryoprotective function which is on par with that of 10% DMSO, but offers the benefit of being less toxic. We will now endeavor to determine the role of cryoprotectants in the maintenance or loss of Treg suppressive function after cryopreservation. A cryoprotectant which is especially adept at maintaining the Treg suppressive function will be ideal for cryopreserving therapeutic cells. We will also continue in our pursuit of greater understanding of Treg cryobiological properties as it remains an understudied topic, and we'll do so with interrupted freezing and stop flow calorimetry techniques. Our efforts in working towards an optimized Treg cryopreservation protocol will allow for the generation of greater numbers of therapeutic Tregs available for cell therapy, ultimately making tolerogenic Treg therapy more sustainable and more feasible for transplant recipients. I'd like to extend special thanks and acknowledgement to all co-authors and colleagues. I'd like to say that although I am absent today, I will be present at the meeting tomorrow in person and will be very glad to take any questions. Similarly, my supervisor, Dr. Esme Dijke, is present today and would also be very glad to discuss this project. Thank you very much for your time and attention.